A lot of them. So let's get started. So it's a real pleasure to introduce Professor Murali. He's a Dean's Chair Professor in the main say Department of ECS. ECS. Yeah. And in the Department of Computer Science at University of Southern California, USC. He currently holds the Rukmini Sri Gopalakrishna Chair, visiting chair professorship in ISC. He's been here for quite some time now. And he's the founding director of the Real at USC Meta Center, which is focused on research and education in AI and learning, and the co-PI of the Discover NSF Expedition Center, focused on superconducting technology. He has been inducted, I think, to the Hall of Fame for 3 of the prestigious computer architecture conferences. This means served as the technical program chair for FPCA 2021 and served as the general co-chair for ISCA 2008. This is fantastic. Prior to the appointment at USC, he worked at Intel, research lab from 2001 to 2007. His work at Intel led to the first CPU-Microarchitecture paper and also influenced Intel's Turbo Boost technology. In 2020, he was a visiting faculty scientist at Facebook, where he designed checkpoint system for distributed training. Murali co-authored Parallel Computer Organization and Design, a widely used textbook to teach both the basic and advanced principles of computer architecture. Murali received a PhD degree in computer engineering from University of Michigan, Annavaram in 2001. He's a fellow of IEEE and senior member of ACE. Good afternoon, everyone. So I assume I don't need to use a microphone. The last row can hear me properly. Yeah? Okay. So unless somebody wants me to use the microphone, I will probably just live without one more piece of technology on my head. So it's my real pleasure to talk to you about some of the work that we have been doing on superconducting CPU designs. And it's part of what we call the Discover Expedition, which is a large NSF program that runs for 7 years, which started in 2022 April, focused on superconducting CPUs. And so for those of you who are interested in superconducting designs and superconducting technologies, you can check more information at the discoverexpedition.usc.edu. And so today what I thought we'll do is I play one of the co-PI roles in this expedition, and my focus is really on a part of that whole design principle, which is focused on the superconducting CPU designs. And here SFQ stands for single flux quantum systems, which is basically a particular type of superconducting technology. And so with that brief introduction, let me jump into the core of the talk. So if you look at CMOS technology trends, what you see here is that there is an unprecedented increase in basically internet traffic, and also correspondingly increase in server shipments across the entire industry. And so you can see that while the number of shipments have grown, correspondingly it doesn't come for free with respect to their energy footprint. The energy footprint has been dramatically growing. And in approximately 2014, 2.5% of the US total energy consumption was used just in managing data centers in the United States. So if you take all the personal computers and other computing infrastructure, you are talking in terms of a very large amounts of energy consumption. And of course, energy consumption also leads to substantial amounts of carbon dioxide and other kinds of detrimental environmental effects. And so these trends are basically unsustainable. And the reasons for that is obviously, for many of you, it's pretty clear, which is that the CMOS technology has been developed for many decades. And there were 2 friends to CMOS technology. One is the Moore's law, and the other one is the Dennett scaling. Moore's law basically allows you to double the density of transistors in a unit area every 18 months to 2 years. And then a lot less well known is the Dennett scaling. Dennett scaling says that the voltage of the operating voltage of a transistor
reduces as you shrink the transistor. It's one of the few things in life where you get to cut the cake and actually also eat it too. But obviously, every good thing has to come to an end, and Dennett scaling actually has been slowing down to an extent now that if you see the operating voltage of the transistors, it hasn't gone down substantially over the last maybe 5 to 10 years or so. And so when you have, but the Moore's law is continuing to reasonably sort of figure out how to pack more and more transistors. But the problem is when you try to pack more transistors without substantially reducing the transistor voltage, your power density is going to be your main enemy. And hence, density without Dennett is basically asking for trouble in the thermal and power domains. And so this is basically the reason why there is a substantial sort of renewed interest in technologies that are beyond CMOS to continue our innovations in computing. And obviously, beyond CMOS, many technologies have been competing in this space. To the right of that picture, to your right, is basically the optical computing. Then more recently, molecular computing has been proposed. And what we have been working on is what is called superconducting CPU designs or superconducting technologies as an alternative or as at least a augmentation to CMOS technologies. And so what is the advantage of the superconducting technologies? The advantages are obvious. If you look at this graph, what you see here is the CMOS-based liquid-cooled Fugaku supercomputers' performance in terms of number of flops per joule. Flops are floating point operations. So this basically think of as like number of additions I can do or a multiplications I can do per joule of energy burned. And so you can see it's approximately 15 gigaflops per joule. If you look at a RQL-based superconducting computer, if one can build it today, it will roughly produce 500 gigaflops per joule. So that's approximately, in the ballpark of 30 times to 40x better in the case of the traditional general purpose supercomputing systems. But if you actually look at custom design systems where superconducting technology is going to become very popular. So custom design systems, for example, include, say, machine learning accelerators. So if you look at the NVIDIA's Ampere, which is a A100 GPU, it produces approximately 2.5 teraops per joule. But if you actually take the AQFP, which is a kind of a superconducting technology, adiabatic quantum superconducting technology, it can produce something in the ballpark of 285 teraops per joule. And so this particular design is actually implemented by some of our colleagues in our expedition team, and they have demonstrated how to build a neural network engine that can produce 285, somewhere in the ballpark of 285 teraops per joule. So now if you look at this, now we are talking about 2 orders of magnitude increase in your teraops per joule energy that you can burn. Yes. So these are basically different kinds of superconducting technologies, basically. Yeah, there are different ways of implementing superconducting, and AQFP basically stands for adiabatic quantum technology, which is a particular way of implementing superconducting. It's TOPS means tera operations per second. So the gigaflops, so this is basically giga floating point operations per second. This is tera floating point operations. But in the case of machine learning architectures, usually they don't have a lot of floating point operations. They tend to be integer or fixed point operations. And so we don't use the notion of flops for neural networks. Instead, they just call them ops, which is just a more narrowly scoped operations, which are simply integer operations. That's general purpose. On the top one is that's why I said that this is basically for a general purpose computing system that will perform, your Microsoft Word documents, for example, whereas this is a custom computing system designed for neural network implementation, primarily inference in this particular example. Okay, so then when you look at these numbers, one can say, what is this fuss all about? Gigaflops per joule is actually quite phenomenal, right? When one can say that this is pretty good already. But the problem is our appetite for flops is unending. Because if you look at the neural network, for example, just take one application domain, and you look at the total number of petaflops that particular model took to train that one model, and this is approximately, it ends in about 2019, which many of you heard of AlphaGo, which is a machine learning model that is used to play the game, AlphaGo game, it took something in the ballpark of 1e⁴ petaflops of operations to actually train that model. And of course, Google would never release the exact cost, but it is expected that training such a system would cost in the orders of several $5 to $10 million US in terms of its energy management and all the other costs associated with the system. And so there is even if you are looking at gigaflops per joule, it's simply not going to be sufficient for the operational density that we're expecting in these large scale machine learning models, just as one example. But that applies to other models too. If you look at, say, weather modeling, climate modeling, all kinds of models require massive number of petaflops. And in fact, there's a huge push to get exaflop machines into the play today, because there is a reason that exaflops machines can actually solve problems that we can't yet solve today. And for people in physics, you probably know better that there are lots of models in physics that actually require massive amounts of computation that we can't do today in a reasonable cost. So given these considerations, at USC, we have been working on something called DISCOVER, which stands for Design and Integration of Superconductive Computations for Ventures Beyond Exascale. And so this is the project that my colleagues, Masood Pedram, myself at USC, and several other colleagues have been collaborating on. And the DISCOVER expedition is an NSF expedition over 7 years working on different aspects of superconducting technology. And so we have people who work on materials and devices, people who work on architecture and design tools, and then people who work on circuits and interfaces. And in the end, our goal is actually at the bottom left of this figure, which is showing you a superconducting SoC, which we call SuperSOC. And the idea here is that we can take a superconducting technology and integrate CPUs, neural network accelerators, and connect it to some DRAM and build an entire system that we can actually demonstrate the feasibility. So this is our 7-year goal, is to actually build a fully operational system that can actually that can integrate a CPU with some machine learning accelerators and icing machines and things of that nature. So that's where the whole talk's focus is. The focus here is of this whole system. I'm not a materials person. I'm not a design or circuits person. I know how to build CPUs. And so we're going to focus on the super CPU design, which is a superconducting CPU technology that we will use as the foundation for the CPU architectures. Everybody with me? All right. In terms of this, it's interesting to actually see the storyline of the CMOS and superconducting technologies to see where we are in superconducting with relationship to the CMOS technology. So if you look at CMOS technology, actually superconducting was discovered before the CMOS designs. But the problem is there are lots of issues that I'm going to talk about. There is a massive investment in the orders of hundreds of billions of dollars in CMOS to accelerate the CMOS design and the integration capabilities. So if you look at it, for example, somewhere in the ballpark of 2000, the 180 nanometer bulk CMOS, we could produce a 1 gigabit DRAM chip in 2000. And then continuing down, you can see that we are now in the ballpark of 7 nanometer regime, or maybe even 5 nanometer regime in the CMOS scale. If you look at what has been done on the to the left-hand side, which is the superconducting technology, the best known designs in superconducting have actually taken off more or less in the last 7 or 8 years, because there's a substantial government funding to actually boost the superconducting technology as a viable alternative or an augmentation for CMOS. And so we can see we're right now around 350 nanometer technology, equivalent technology, roughly speaking, in terms of the size of the devices. So we're about 20-something years behind CMOS if you compare it from the density standpoint. And so there's a lot of room to actually grow and a lot of innovation that needs to be played in the superconducting space in order for us to kind of get closer and closer to the CMOS domain itself. And one of the key criticisms that people have pointed to us when we talk about superconducting is that superconducting is very expensive because there's a lot of cooling requirements, because as I'll show you a little bit later, superconducting requires that the devices be operated somewhere between 4 to 6 Kelvin, which is very, very low temperature. And so it's not necessarily as cold as the quantum computing devices, but it's pretty close. It's very, very close to the 4 Kelvin, 6 Kelvin. And so the cooling cost is enormous. And so what we have plotted here is the total power in megawatts. And on the x-axis is the performance of computing systems in petaflops. And the dots are showing you various computing systems that are produced by the various competing agencies from the Chinese companies, the Japanese companies, and the US companies. And this blue line is the projection of what the superconducting technologies will consume in terms of the power, total power, including the cooling costs. And so if you look at roughly the exascale kinds of computation, which is roughly to the very right of this figure, you are talking about roughly 1 megawatt of power for an exascale of computing, which is phenomenal actually. Because if you want to do an exascale today, you're talking in the orders of 100 megawatts or 200 megawatts of power. But this systems built on a superconducting technology, including the cooling costs, can operate around 1.5 megawatt, which is a huge improvement if we can successfully sort of come over the hurdles that I'm going to discuss. So hopefully with that set, what I wanted to talk about is a couple of things. I didn't know how many of you knew what superconducting technology or SFQ devices look like. How many of you heard of it? Good. So given that not very many people are familiar with the SFQ technology, I know a lot of you are quantum people. And unfortunately, superconducting technology, particularly SFQ, single flux quantum, somehow reminds you of quantum devices, but they are not quantum devices, completely different principles that they operate on, but just coincidentally, they have that name. And so I thought I'll spend a little bit of time talking about the SFQ technology and the logic and circuits behind the SFQ technology. And I think this is really the key element to understand what we're actually currently doing. And then I will talk about some of the innovations that we have been working on within our expedition team. And even if I don't get to a lot of the details there, which may very well be, at least I would have conveyed to you the message of what is in the SFQ and why is it important. Okay, so SFQ technology, what's inside that? By the way, that picture is basically a liquid helium tank, which will basically cool the chips to close to 4 Kelvin. And it's in one of our collaborators' facility in Yokohama. And so what's in the SFQ technology? So the SFQ technology basically can be thought of as from starting with a very simple Josephson junction. We can start building what is called SQUIDs, which are superconducting quantum interference devices. And then from there, I'm going to talk a little bit about Josephson transmission lines, and then finally talk to you about destructive readout cells, which is basically the small memory cells that you can build. So these are the 4 things that I want to sort of convey to you what is behind each of them. So a Josephson junction is basically 2 superconducting materials that are separated by a very thin sort of a oxide layer. And when you cool these superconducting materials to around 6 Kelvin or so, basically it forms what is called the Cooper pairs. And they're basically a set of electrons that can move through as if there is no resistance. And I don't mean some small resistance, no, 0 resistance. What that means is you can actually push these electrons through for long distances with 0 energy move in the movement of the electrons themselves. And hence, this particular phenomenon has been observed in the early 1900s itself. And the idea of using these as a terminal devices to do computing has only recently been developed. And so this is basically what is called a single flux quantum technology, and essentially the Josephson junction, which is these 2 superconducting materials separated by a thin oxide layer. And this is the foundational element, which is equivalent to a transistor in a traditional CMOS device. And when the Cooper pairs, when they're moving, when the current is actually small, which is some kind of what is called a critical current, IC, then the JJ behaves like a superconducting material. The interesting property is that when the current is large, JJ loses its superconductivity, and we call that particular system a switched Josephson junction. So what I show in this figure here is that as the current IC continues to increase on the y-axis from 0 towards the top or 0 down towards the bottom, for a substantial amount of time, till you reach this IC value, the voltage does not develop because there is no resistance in the system. But when the moment you touch the IC, suddenly the voltage appears across these junctions. And hence, you can see that as long as the current is below the IC level, there is no voltage, and then suddenly the voltage develops when you increase the critical current. So this is the foundational principle that is going to be used for building all kinds of complex circuits from here on. Okay, so the first complex circuit that I wanted to talk to you about, which is built on the Josephson junction technology, is called the Josephson's transmission line, or JTLs. So from going forward from here on, whenever I show you a picture with an X marked on a line, that X corresponds to a Josephson junction. There is one Josephson junction in that particular phase. And of course, you know these L1, L2, L3 from a traditional electrical engineering perspective are basically inductances. And so the Josephson junction, as shown in this particular picture, basically you have J1, J2 with a bunch of inductances together, forms what is called a squid loop. And I will explain to you what this is going to do. What this allows us to do is that any voltage or input current that you provide on the input side is nicely transmitted onto the output side. And how is it done? The way it is done as shown in this very simple animation. Let's say that there is an input voltage pulse is appearing on the input. So how did it get generated? Somebody produces the input and gives you that input. And the moment the input is provided, but let me step back 1 second. Before I do that, if you see, there is IB1 and IB2. These are the two currents that are actually provided to these two Josephson junctions. These currents, IB1 and IB2, are carefully selected such that these two values are less than the critical current. And because they are less than the critical current, the Josephson junctions J1 and J2 behave like a superconducting materials without any switching at that point. And now let's say there's an input voltage has appeared. Because there's an input voltage that has been generated, essentially what happens is that the Josephson junction J1 essentially receives an additional boost of current into its junction. And because it receives an additional boost of current into its junction, effectively it now goes above the critical current IC. And because it goes above the critical current IC, what happens now? This will switch. Because this will switch, there is a voltage that appears at this junction. And because there's an inductor, basically you'll get another voltage pulse on this, a flux pulse on this. And because there is a pulse that appears on L2, the next step, effectively, there's a current that flows to J2, and the J2's current also increases. And because the J2's current also increases above the IC, J2 switches. And so now when the J2 switches, essentially there's a voltage pulse here, and that will basically allow the voltage pulse to actually transmit on the output side. So this is called a transmission line because it's essentially allowing an input to be sent to the output through this series of Josephson junctions and inductors. And it allows us to essentially think of them as repeaters. Imagine that this signal input is relatively weak. You can boost the signal by a repeater like they were designed by allowing this Josephson transmission line. Yes. Oh, the inductors are required because you're essentially generating a magnetic flux from the voltage that you're providing. And that's the magnetic flux that's actually going to be, these voltage pulses basically are basically little magnetic fluxes. So when the junctions switch, so the question is, for those of you on the online, when the junction switches, does it dissipate heat? I think that's the question. Yes, they do, but it turns out that because these currents are so small, I don't have the exact number, the amount of heat that they generate in the process of switching is extraordinarily low. And now, built on the JTL, which is the squid technology, you can see that you can actually see in this particular picture, this is what is called a destructive readout cell, which is a kind of a memory cell that allows you to store a number, store a value. And so the way we store the values is in the form of a flux or a magnetic pulse. And so if you look at this picture and the previous picture, you will see a lot of similarities. The J1, J2s exist, IB current exists, and there is a input inductance. All of those things exist, except now they have slightly added a few more components. There's a new junction, Josephson junction J0, and a Josephson junction J3. This is the schematic of a destructive readout cell, also called the DRO cell. And this is called destructive readout because once you read this cell, the stored content will actually dissipate and it is no longer stored in the cell. And so let's look at what this operation of the circuit would look like. And again, the principle is very simple. You have these bias currents, IB, which is providing to this Josephson junction. And there is a little bit of a current that appears on the Josephson junction J2 and J3. But all these currents are less than the critical current, which is required when they're initially operating. And now let's take a look at what happens when this is going to receive an input. So when the input voltage pulse appears on the, when there is a voltage pulse appearing on the input side, which is this D side, then the current through the Josephson junction J1 increases and exceeds the critical current. This is the same principle which we applied in the squid design. And because of that, basically you will cause a pulse to appear on this L2 area, and it will cause a certain amount of current to flow through J2. But here is the interesting thing. Even after adding the new current that goes into J2, the total current going in through the J2 loop, the J2 junction, is still less than the critical current. Because it is still less than the critical current, this junction does not switch. J2 does not switch. And as a result, what happens now? You have a magnetic pulse that was originating at this junction right after J0, but it cannot escape because J2 cannot switch. And so what happens now? That pulse is now stored as a loop inside this J1, L2, J2 squid. And what does that mean? As long as there is no other external stimuli, that pulse is stored there, and that pulse storage can be treated as the storage of a single value, let's say a bit value of 1. And so the pulse will appear. In this state, the squid will trap, we call it a trapped squid. It stores a magnetic flux quanta, and it is now considered a value of 1. So now you can store something in this circuit now, right? So now you can see where we are actually leading towards. We're now leading towards building a system, a digital system that can move data through the JTLs, store zeros and ones through these DRO cells. And once you have them, you can put them a few of them together, and you can start building complex circuits from these basic principles. And so this cell, now that this is switched and it has a squid, there's a trap. The squid has trapped a junction, a magnetic flux. This is considered to hold a value of 1. Now, at some point, you want to read this value. How are you going to read this value? So the way you read this value is, you see there is a particular, in this particular circuit, there is something called the clock input. So we are going to put a clock input into the circuit. And when you put the clock input into the circuit, what happens now? You are essentially providing an additional current going through the J2. And now the J2's current exceeds the critical current. And because the J2 current exceeds the critical current, if there was a magnetic pulse already stored here, it will cause a trigger, this pulse to release itself and go out on the Q side. This is exactly the principle of a DQ flip-flop. For those of you who are familiar with the traditional CMOS design, it's like a flip-flop, right? Like you basically store, it stores until you provide an additional external input, and then the output comes out on the other side. And so when the current comes through, basically the J2 will switch. And once the J2 switches, the pulse is released. Now you can read the value of 1. Yes. Input side? No, because the Josephson, in order for it to, so the question for those of you who are online is that, will the pulse dissipate, will the pulse release on the opposite direction? But remember that there is no critical current on J1, and therefore there is no way for it to escape, because it's basically stuck between 2 junctions which are below the critical current, and therefore it cannot. Right? And so you can now see that it looks like a flip-flop. You can actually store values and release values. And so, and it turns out that if you actually, so this is basically reading a value of 1. This is equivalent to reading a value of 1. And now let's take a look at what happens if the DRO state, if the squid actually does not store anything. There's a no 0, it stored 0. What happens now is that when you provide a clock input, the Josephson junction DA3 will in fact switch, and that switching allows the current to basically go to ground, and effectively no voltage pulse is actually generated on the output of Q. And so either it will produce a 1 output if there is a squid loop that has trapped a magnetic flux, and if there is no magnetic flux, Q produces no output in this case. And this is basically a 0-1 output operation of the DRO cell. And so, and then one other important point that I wanted to mention is that if there is already a pulse stored, and this is called a destructive readout single bit storage, if there's a magnetic pulse that, let's say that there's another input coming in while there is a value already stored. In this case, what happens is that the Josephson junction J0 will switch, and it allows basically the current to dissipate, and it provides it holds the previously held magnetic flux, and the newly incoming input is actually dissipated in this case. And therefore, you will be protected from unnecessary inputs that are coming in, and you will still be able to store that value. So this is basically the operation of a DRO cell in the superconducting space. Okay, so with that being said, this is why it's called as SFQ technology, because the information is stored as a magnetic flux quanta and transferred as a single flux quantum voltage. And it's a very, very small voltage. And this technology is called SFQ, or single flux quantum technology. And these voltage pulses are so small that these SFQ technology systems cannot directly communicate and operate with CMOS, because CMOS voltage pulse requirements are substantially higher voltage pulses than the SFQ voltage pulses. So in fact, there are what is called interface circuits that allow you to communicate basically by magnifying this voltage pulse, and then you can talk to the CMOS technology. Otherwise, these pulses are completely different orders of magnitude voltage pulses than CMOS, which is also the reason why the SFQ technology is substantially lower energy than the CMOS technology. Yes. Are you talking to about the previous slides where whether there is stored value or not stored value? That's the difference you're talking about. When you say case one, what is in the Joseph transmission line? I think I understand. So the question I think that asking is, in the case of a Josephson transmission line, how come the input voltage pulse can actually jump through J1 and J2 and exceed and exit on the output side, whereas with a DRO cell, why is it trapped? The magic is critical current, exactly. The critical current applied to IB1 and IB2 is already very close to the not critical current, the bias current, I should say. The bias current applied to the Josephson junction J1 and J2 is already very close to the critical current. So even a small increase in the current coming into these junctions will cause both those junctions to actually switch and allow the pulse to traverse to the other side. Whereas in the case of this particular circuit, IB is a strong bias current, whereas the clock has very little current going through. And as a result, that pulse gets trapped unless there is an external, think of this as an additional bias current boost that you give, right? So the clock actually acts as a programmable bias current. And that programmable bias current is what allows you to read or not read, store or not store. Make sense? Yeah. So this is volatile, obviously, right? I mean, basically, in fact, forget about even being volatile. If the temperature raises above 4 Kelvin, the machine no longer operates, right? It's not about power loss. Even thermal losses cause the system to leave the superconducting space. And second, this particular circuit stores 1 bit. And of course, you know how to build. It's the same with the CMOS 6-transistor cell, stores a single bit of information. And then you can build many of those packs together to create a much denser memory that you need. Okay, so with that background yeah. Maximum clock frequency. So SFQ technology has been demonstrated in lab settings to operate approximately at 100 gigahertz, right? And so these systems can clock at a much, much higher frequency than any existing CMOS devices. The dimension of these circuits, I don't remember, but roughly, as I said, it's in the ballpark of about 100 times. Each of these Josephson junctions is 100 times the size of the current transistor size, which is the 5 nanometer transistor technology. But I don't know the physical dimensions. But I know relatively, these are 100 times bigger. And MIT Lincoln Labs actually has a facility now that actually fabricates these for universities to produce superconducting, small superconducting chips, something like 5 by 5 millimeters, like a 25 square millimeter chip. Correct. The only way to manipulate the state of the system is put through a clock. Then you release the pulse, right? But when there is no pulse, you have to, when there's no stored pulse, then that pulse will get stored. Okay, so with that, I want to just kind of jump into a little bit more detail of the sort of the next level of abstraction, which is how do you build logic circuits from this, logic and circuits from this. And so, so let's take a look at some example circuits. Here is an SFQ AND gate, and here is an SFQ OR gate. They don't look anything like the existing CMOS-based AND and OR gates, if you're familiar with AND and OR gates in CMOS. But this is how AND gates and OR gates look like. I don't have the time to go through it, but basically you can see that if you put A and B to as inputs, two input pulses, and the clock, when the clock pin is read out, the output will be the AND of the A and B. And then in this particular circuit, the clock is the external impetus. And so if you put A equals to 1 and B equals to 0, and when you put the clock through, the output, we will see a 0, we'll see a 1 pulse generating on the output. So this is roughly speaking the operation of an AND and OR gate. But what is important to recognize is that these are expensive compared to traditional CMOS transistor-based technologies. Simple logic gates like ANDs and ORs read a lot of Josephson junctions. And why is it important? The density of the current manufacturable systems we expect within the next 3 to 5 years will have no more than 1 million Josephson junctions at best, right? And so if you have a single AND gate that takes up, I forget, 12 JJs, that's a lot of JJs to use in your very limited Josephson junction budget. Okay, so there are a few things that I wanted to mention as the challenges for those of you who are interested in this space. From a computing standpoint, what are the biggest challenges? Almost all the SFQ logic gates have a clock. If you have seen, AND gates in CMOS don't have clocks. OR gates don't have clocks. Whereas in the Josephson junction technology or SFQ technology, every gate has a clock. There are a few exceptions, but the vast majority of the gates need a clock. And as a result, this is called gate level pipeline systems, not pipelines at the latches. Like, for example, you can, for those of you who are familiar with the CPU design, there may be an entire arithmetic logic unit which will perform an add, multiply operations. And then there is a latch on both ends. And only the latches need to be clocked, but none of the gates in the middle of the circuit. Whereas in the case of an SFQ, every gate needs to be clocked, with the exception, as I said, of a few logic gates. That's a huge problem, right? Because if you have this huge network of clocking that has to go to every single gate in the system, that is going to consume a substantial amount of clocking network that needs to be built in the superconducting CPU systems. That's one. Second one, there is a need for path balancing as well. So let me explain what the challenges are. So because we are a gate level pipelining, and what happens now is that, imagine that you have these two series of AND gates, AND1 and AND2, and they're taking this is a standard cascaded AND, like it's equivalent to a 3-input AND gate, right? So you do an AND of 2 inputs, produce that, and produce the output on the AND. In a traditional CMOS, no problem. You put the 2 inputs to the AND first gate and input to the second gate. And whenever the output of the first gate comes, it comes, and AND2 will take that and produce the output. There is no need for any special logic here. But here is the problem with SFQ. These AND gates have clocks. And as a result, when you send a clock to these systems, this is what the system is going to do. So the As soon as the two inputs are 1 and 1, and this is 1, this is 0 at the beginning, right? This is before anything has been done, the output of the AND gate is 0 first, and these two are 1. And unfortunately, the first input pulse, as soon as the clock is sent out, will produce this AND will instantly trigger and produce a value of 0, and the value of the 1 from these first two inputs will come. This is called path balancing, because every input coming into the gate must come through the same number of clocks in order for it to reach that point. If it takes different clocks to reach that point, you will end up with this asynchrony that I mentioned, which will cause the system to not operate correctly. And how do you solve this problem? The way you solve that problem is the DRO cell, which is basically your flip-flop, which essentially holds that circuit, that input pulse for its extra clock, and then delivers it in conjunction with the first set of A, B inputs that are being produced. And so if you have that DRO circuit, basically what happens is that when the inputs are coming through on the first clock, the 1 and 1 will go through, but the second C value is actually delayed and comes to the output of the DRO on one cycle later. And by that time, AND 1 would have finished. And then you have the right operational point, which is the output. This is a huge problem for circuit designers because in CMOS, you're not used to thinking in this way. And so you have to deal with path balancing of the circuits also. There's another problem. SFQ logic, unlike CMOS transistors, CMOS designs, they don't, it's not like you can take a magnetic flux and say you both can share it. There is no notion of fan out in SFQ. What is a fan out? Fan out is when a gate can drive 2 additional gates or 3 additional gates or 4 additional gates. That's what is called a fan out circuit, a fan out design. In the case of SFQ, fan outs are not free. Every fan out must be explicitly, you take a pulse and you must replicate it to generate it across the places. And that's what is called a splitter cell. This is an example of a splitter cell, which takes one input and produces the 2 outputs, which can then feed to 2 separate circuits. And so splitters are zero cost, non-zero cost. Mergers are the same thing. If you have 2 inputs coming in and you want to merge them, you have to explicitly allow a merging circuit to work in between. So this is the merge circuit design for the SFQs, right? But luckily, these don't have any clocks. So because as a single input comes in, as soon as the input comes in, this will actually propagate automatically without an additional clock. So this is an example of a clockless SFQ gate that I was talking about. So the next thing that I want to say is where do we stand in terms of the SFQ superconducting microprocessor design? So some of the most well-known microprocessors that are actually built are very, very tiny baby designs. For example, this is, I think, a chip design of a Core E4 processor, I think, which was published approximately, I forget the date, 2016, not very long ago. And the processor is very basic. It's an 8-bit serial microprocessor. For those of you, what is serial microprocessor? You want to add 2 8-bit numbers, you pump 1 bit at a time. After 8 cycles later, you'll get the output. That's a very, right, this is what I think in your 101 class in your undergraduate days, you probably would build something like this in ECE. And so this is what they built. This is state of the art in 2016. It has 4 8-bit registers, which is a really small number of memory cells, basically. And the part of the problem, as I said, is that Josephson junctions are really a hindrance. You don't have a lot of Josephson junctions. And it has a custom-built 20 instructions in the system. So it can only do 20 specific instructions in the system. And about 7,000 JJs, right? That's what the system was built to. And so from here, what we're trying to do is to build a much more complex CPU design going forward, and enabling that is sort of a path filled with thorns and bushes and marshlands and everything in between. And so the 2 things that we are currently working on now, I have maybe about 10 minutes I wanted to talk. Yeah. Simple CMOS. That's a good question. I didn't think of it, but I don't know on the top of my head. I don't want to give you a wrong number, but I don't have a sense of what this would cost in CMOS today. I think that's the question you're asking. I don't have. Yeah. I don't have that in my mind. So for the next maybe 10 minutes or so, what I wanted to do is to talk about some of the specific technologies that we have been working on. the two things that we have been working on is memory, because memory is virtually non-existent because this is all flip-flop based designs. And so for those of you, again, who are very well-versed with CMOS designs, you know, you build a SRAM transistor-based cell with 6 transistors. Whereas here, the only way to store data is through DRO cells, and the DRO cells are very, very expensive in terms of Josephson junction count. And hence, most memory that can be integrated onto these SFQ-based processors is supposedly going to be very small, few kilobits. And if you look at microprocessor pictures today, megabits of memory is actually on those microprocessors. Branch predictors, huge amounts of data is there. Caches, huge amount of, not data, data storage capabilities are there. Caches, huge amounts of data storage is there. And so one of the challenges is that how do you actually increase the memory density of these systems? That's one of the challenges that we've been working on. And I'll touch a little bit more detail on that one. And then the second one is how do you deal with very deep pipelines? So if you look at a CMOS-based CMOS processors today, 20 pipeline stages, 16 pipeline stages, somewhere in that ballpark today, whereas the best designed SFQ microprocessor is likely to have something in the ballpark of several hundred pipeline stages. And there are lots of challenges in that, but I'll come back another time and talk about that, but probably we're going to spend a little bit more time on the memory side of the things. Yeah, in fact, there are like interesting ways of like, there are a lot of circuit. I'm not a big circuits person, but there are lots of interesting circuit optimizations and implementations where people are implementing these designs, not using the CMOS equivalents, but something else as an alternative strategy. So the first one that I want to talk about a little bit again for a few minutes is called multi-fluxon storage. This is something that we invented about 2-3 years ago. And the idea is very simple. If you look at destructive readout cells, which is a circuit I just told you before, the advantage is that this cell is relatively small, but the disadvantage is when you read the data, it dissipates, it's gone. But in CPU designs, every data that you read is non-destructive. By definition, most SRAM bits, you can see read an SRAM cell, it's not going to go away, right? So this destructive readout cell makes it very hard to design processors because register file, if you do R1 plus R2 equals to R3, you read register R1, you read register R2, you stored in register R3, and you expect to reuse those registers R1 and R2 again in a future computation, but that's gone. You can't reuse them. Once you read, it's over. So people actually started to think about what can you do? So the non-destructive readout cell looks like this, a massive monster, right? Much, much bigger than a destructive readout cell. It consumes roughly 3 times more area. And again, in SFQ technology, area is simply Josephson junction counts, the total JJ counts. And so it's much more expensive to actually use NDRO cells. And or if you use DRO cells, this is not great. And so one of the things that we noticed is that the problem, one way to implement this as a multi-fluxon storage is that if you look at this picture, I told you that J0 prevents the accumulation of multiple loops of data inside the squid loop. So what we did was we actually implemented a full circuit of a full cell design where we eliminated J0, appropriately adjusted the L1, L2, and L3 inductances, and adjusted the bias currents. And we can actually, now you remove them, it allows you to send multiple inputs into the system, and they all get stored into the squid loop. And now you can actually send 1 pulse, 2nd pulse, 3rd pulse, and you can actually store 1, 2, 3, all of them inside that loop. And then you can create essentially equivalent to a multi-bit storage in this particular configuration. So now I can create 2 bits equivalent of information by storing, let's say, if I want to store 2, I will have 2 fluxons. If I want to store 3, I'll have 3 fluxons. And of course, 3 is represented as a bit pattern of 1, 1, right? Like on a binary scale. And therefore, you can consider it as a 2-bit storage system in this case. And so this is basically what we have actually implemented and then fully simulated the system to create a multi-fluxon storage. But this is also destructive. When you read this, the values will dissipate. And so we have solved part of the problem by essentially doubling the density of memory, but we still haven't solved the problem of how to actually keep the values, continue to reuse them many times going forward. And so I'll talk about how to solve that in just a few seconds. Yeah. These will be voltage pulses. Once you read, they will look like small voltage pulses. These are circulating inside, yeah. Yes, they have 3 different pulses and 3 different, correct. And therefore, just to finish that question, if you want to read how many pulses are there, you must provide 3 clock pulses to know the first bit, the second pulse, the third pulse. They will all come out serially on the output side. So your clock will also has to understand the notion of 2-bit storage, and it has to pump 3 pulses to know that it is actually completely vacated that particular cell, basically. Yeah, you have to have some minimum timing. There's like a hold and setup times that you have to follow in this case. Correct. Essentially that, but the way you think of it is that you don't need all of that voltage to generate the output pulse. And so basically part of it will be used to generate the first pulse, the second pulse, and the third pulse. And so in other words, the clock circuit that you're actually using here, if you put in multiple clocks, you will think of it this way. Virtually, this is how you should interpret that. It's as if there are 3 fluxons that are actually stored, and you send each clock pulse, one of those fluxons will actually be dissipating on the output side. Okay, so with that, do I have an additional 5 minutes? Or yeah. Okay. Okay, so what I wanted to do is to talk about what did we do with this multi-fluxon storage. We have essentially looked at the CPU processors. That's what my area is. And if you look at the CPU designs today, a lot of the CPU designs area is spent on prediction structures like branch predictors and other kinds of structures, and register files. Register files is where you store, like I gave you the example where you say add 2 numbers. The way you do this addition is you bring those data into 2 registers, add those registers, and then store it into an additional extra register. That's what we do in all traditional computing today. And so registers are a big area hogs. There's a lot of area required and a lot of density required in order to build good CPUs. So what we said is, let's go ahead and build a register file using my multi-fluxon storage capability. So basically, I now doubled the density of DRO cells, and I don't want to use NDRO, right? But I still want to preserve the property that when I read the value of R1 and R2, I can go back and reread the value of R1 and R2. And so that led to the design called HyPerf, which is the design of high-performance register file with multi-fluxon storage, which appeared, I think, this year or last year at HPC, high-performance computer architecture. And so let me talk about that a little bit in detail. So it has basically 2x the capacity. Reads are destructive. How do you support multiple readouts? And this is basically the foundation of that work that we were looking at. And so let me sort of talk about the design in itself, because I'm going to skip through because I only have 5 minutes. So the basic design that we have used, I'm going to give you the intuition first. The intuition is I may have 100 registers in my register file, but any one point of time, how many registers am I reading? Any instruction will read 2 registers, maybe 3 registers, depending upon your instructions or architecture. And therefore, you only need this non-destructive capability on those registers that you just read. That's the key. The key is, even though I may have 100 registers, I am not looking forward to keeping the non-destructive property for all of them because I'm not reading all of them. I'm only reading a subset of them. If you're going to read a subset of the registers, why pay the whole penalty of non-destructive readout for all the registers? And instead, what we are going to do is we're going to read the data, lose the content, just like we will traditional DRO cell. And what will we do? We will look at how DRAMs are done. What do you do in a DRAM? When you read a DRAM content, essentially you lost the content. But what do DRAMs do? They recirculate the data back into the into the row that you just read, because that's what is basically called, sometimes also called refresh. You essentially bring the data back in. That's exactly the principle that we applied here. And I will just show you that the picture here shows you the destructive readout cell-based register file. This is, each one is a rectangular box is a register. And then we have something called a refresh buffer or a loopback buffer. Anytime you read a register, those register values are read into the loop buffer, and the loop buffer will write them back into the same register that you just read. That is the key element of the whole design, which allows you to do destructive readout and still enable you to preserve the property of non-destructivity so that you can continue to read these registers. And so this is the principle that we have applied. And so so let me sort of show you as a simple animation what happens. So imagine that there are two. There's a value 1 0 stored in this particular register. 1 0 means number 2. That's basically 2 pulses stored in that one cell. And you generate a clock pulse. So initially you set the loop buffer to 1, and then when you read this register, effectively what happens is those register values go into the loop buffer. The loop buffer will generate 2 output pulses, and in addition, those 2 output buffers will then generate a splits. This is a splitter cell here. The splitter cell causes this data to be produced into 2 copies. 1 copy is sent to the ALU, and 1 copy is sent back to the register. That's the basic principle behind this design. I know I skipped through some of the slides just to get through the presentation without taking up too much of your time. And so this design was fully implemented, and we have shown the improvement in density, as well as there's a little bit of a latency penalty, because now every register read has to go through the loop buffer. So it's on the critical path of your read. So anytime you read, it reads from the register, buffers here, splits there, and then goes back. And so there's a performance penalty associated with this design potentially. And so we wanted to measure some of the statistics. And so in terms of the total JJ count reduction for a large register file, we can save approximately half of the registers, half of the Josephson junctions. And in terms of power consumption, we can substantially reduce the power consumption again by about half. And in terms of the readout delay, you see, this is the penalty we pay. We are approximately 8% more latency to access the register. So if it takes you 100 picoseconds, it will now take you 108 picoseconds. That's how you want to think about it. So there's some additional latency cost associated with this design. And we showed you what does that impact? Like if the latency of reading the register is high, does it automatically cause the applications to also be slowed down? It turns out that the applications have a natural tendency to deal with some slowdowns. In terms of the application performance, you don't lose 8%, you lose approximately 3% in your net. This is important because from an end user perspective, if you're running an Excel spreadsheet, it will load 3% slower, not 8% slower. That's how you want to interpret this result. And so that's the design that we have implemented. And as I said, well, if I have more time, I will talk about some of the other designs in the super branch predictor designs that we have been looking at, and other cachely related structures. So there's a whole plethora of research that's out there that needs to be discovered and that needs to be innovated. And with that, as a concluding thoughts, what I wanted to show you is that the architectural implications of SFQ technology provide lots of exciting challenges. For those of you who are in sort of the computer systems and engineering side, you would see that this is a great area. And just beginning this journey. And as I said, if you're interested in learning a little bit more, discover expedition.usc.edu. And in fact, the Discover has actually a lot of dimensions that we have been exploring, not just on technology side, but also broader reach. We have high school students who are going to come into our labs and experiment with some of the cold new labs that we are building with the liquid hydrogen and liquid helium labs that we're going to use. And so there will be a lot of exciting things that will develop. With that, I'll stop. Three pulses. Right, because basically you read it as a decimal equivalent, right? Like, so you, and then you have to read. That's the slides that I kind of skipped over, which is how do you take 3 pulses and then a value of 3 and then code that as so that's what we're going to do. Yeah. What's the size of the pulse? I think I don't remember from the top of my head, but I will have to. If you email me, I will send you that information. So currently, I believe the MIT Lincoln Labs, because we are not the fabrication people, MIT Lincoln Labs, I think, uses niobium as one of the superconducting materials.
For performance, same thing that we said in the beginning.
Well, so the Yokohama facility is actually a physical test facility. We can actually build tiny chips and actually do physical measurements. The results that I showed you at the end are based on simulation results that we have actually built on top of. Yeah, that's what I said. It's a simulated performance of the system, but not actually on the Yokohama test facility. I don't. I mean, these are numbers that I don't keep in my head, but these are available. Yeah. I have them, but one of the things I will do is maybe I'll post the slides and then I will put those numbers on. Yeah. Yeah, so there are some interesting. So we're trying to. The question is, does it have software implications? So this technology will have, ideally speaking, some amount of software hardware collaborative development would be ideal. But the way we have been treating it is, software people, we are not going to change them, right? And therefore, we are going to live with whatever software that is going to be there, and we want to use whatever software people wants to use. And that's the reason why we are going to bend over backwards to build the register files and other things that look a lot like a traditional CPU design. But in practice and in reality, I think if there is a way to also get the software, particularly the compilers and runtime systems, to understand that there are deep pipelines. So you cannot just say, produce and add 2 numbers, immediately use them. You don't, because you want to use the data slightly farther down, because these are gate level pipelines and they will take you 20 cycles to get the result. And so you need to delay the computations production to when it is actually used. Right? But that's sort of in the farther horizon of where we want to look at. Thank you so much.